Alrighty, guys. Let's start Unit 3, stoichiometry. We're going to start from the very beginning. First thing we need to know for stoich is balancing, okay? So I'm going to go through what balancing is real quick, and then I'll teach you my way of doing it. But if you have your way of doing it, do it your way, whatever works, okay? So chemical equation is just a way for us to represent a chemical equation. Basically, it's a recipe telling you that if you react two things on the left side of the arrow, you make the chemicals on the right side of the arrow. And then balancing is just making sure we have the same number of everything on both sides of the equation, okay? So the only thing that we really need to do for balancing is you just need to write coefficients or numbers in front of the molecules, okay? All right, we're going to go straight into balancing. Any questions about that? Hopefully you guys are familiar with that term or somewhat remember how to balance. Okay, so if you guys have your own method of balancing, please ignore me as I go through how to balance 3.1. If you are a little shaky or don't remember, then you can follow along with the way I do it. But if you have your own way, do it your way. As long as we get the same answer, that's all that really matters, okay? All right, so we got this chemical equation right here. It's not balanced. So first thing you want to do is you want to just double check the elements on both sides of the equation. So what I like to do is I like to make a table with all of the elements on the left and right side of the arrow. Okay, so if you look on the left side of the arrow, you have a sodium, Na, you have a hydrogen, and you have an oxygen. And what we want to do is I just make a table counting how many of each element there is on the left side and the right side. Okay, so if I look on the left side, I only see one sodium, so I'm just going to write 1 right here. And then I'm going to see 2 hydrogens right here and 1 oxygen on the left side. Again, if you have your own method of balancing, please use that method, whatever works best with your brain. All right, take a look at the right side. We got 1 sodium, we have 1 oxygen, but we have 3 hydrogens. Okay. So we want to make sure we have the same of every element on both sides of the arrow. And the one that's not balanced is the hydrogen right here. So what we're going to do is we're going to add molecules to the side that has less until they balance out, okay? So if I take a look at this equation, the left side has fewer hydrogens, right? So I need to add a hydrogen to the left side. However, the problem is you can't just be like, hey, I'm going to add a hydrogen like that. Okay, because if you do, you change the reaction. It's not the same reaction anymore, okay? You could think of this as your mom's recipe. You don't change it. You leave it exactly the way it is. The molecules are the same. The only thing you're allowed to do is add more of what's already there. So the only molecule that has hydrogen, the one that we need to add, is H2O. So we're going to add an entire H2O molecule. Okay, so now there are 2 H2O molecules, which means you have double the hydrogen and double the oxygen. Okay. All right, so we added that, but now if you take a look at it, there's not enough hydrogen and oxygen on the right side. So we have to add a molecule that has hydrogen and oxygen. So we're going to add this guy right here, NaOH. That's going to result in us doubling the sodium. We're going to add 1 to the hydrogen. So we got 4 and 2 for the oxygen. So hydrogen and oxygen are now balanced. Sodium's not balanced. So we got to add 1 more, and then we're all balanced out. So basically, we need to add 1 of everything except H2. And the way that we represent that is there are 2 Na, so we just write a 2 in front of Na. There are 2 H2O, so we write a 2 in front of it. And then there are 2 NaOHs, so we just add a 2 in front. And we only have 1 of this, so we can leave that alone. So if you guys notice, I didn't change anything about the equation, right? All I did was put numbers in front of the molecules. That's what you want to do for balancing. Again, the equation is mom's recipe. You don't touch it. You don't mess with it. Leave it exactly the same. All you do is put numbers in front. Okay, so that's my way of balancing. If you have your own way of doing it, but you get the same answer, more than welcome to use it, okay? You don't need to use my way to balance. I won't take it too personal. All right, any questions on balancing? All right, so I'm gonna give you guys maybe about a minute, 2 minutes, 2 minutes. We'll do 2 minutes in order to balance this one right here, 3.2. You can work with the person next to you or by yourself, and then we'll go over it together and then we'll move on. All right, so for 3.2, we're gonna start, I'm gonna start just by counting up the elements. So if you take a look at the equation, you got aluminum, hydrogen, and chlorine. Okay. Left side, you got 1, 1, 1. Right side, you got 1, 2, and 3. Okay. So we're gonna need some more HCl's. And so I'm gonna add an HCl. If I add an HCl, it's gonna get me 2 and 2. But then we need more chlorine. So I'm gonna add another HCl right here. Okay. If I do that, that's gonna get me to 3 and 3. Okay, the problem is now I have to add more hydrogens on the right side. So I'm gonna add H2. That's going to get me to 4. And this is where balancing can get a little bit annoying because we're gonna have to go back and add another HCl. So if we add another HCl, we're gonna get to 4 and 4. But we gotta add more chlorine to the right side. So this one is a very annoying problem. Why did I pick this problem? It feels to annoy you guys, but now I have to do it. Okay, so we got this on our right side. So let's start with the aluminum. We're going to add another aluminum on the left side. That's going to bring our number to 2. That balances the aluminum. Hydrogen looks good, but chlorine is not balanced. You need 2 more to get it to 6. So we're going to add 2 HCl's. That's going to get our chlorines to 6, but that's also going to get our hydrogens to 6. But that works out because if you add 1 more hydrogen, that gets you to 6. Okay, so I'm sorry for giving you guys this problem, but the coefficients will be 2, 6, 2, 3. Okay, so if you guys got that, great job. On the AP test, you will not get one nearly that long. Usually the balancing problems won't go more than 3. Like 3 or 4 is going to be your max for the coefficients. Okay, and if it's bigger than that, they'll usually just have it balanced for you already. And so if you're able to do this, then you should be good on balancing in terms of for the test. Okay. All right. Any questions on that one? I'm sorry, guys. That one is a very annoying problem. Okay, so that is balancing. We're going to come back to balancing when we do stoichiometry later, but before we do, we're going to go into something called percent composition. Okay, so this one right here is going to require you to write down an equation. So I'm going to give you guys maybe about a minute to write this formula down. Excuse me, but basically this tells us that we can find the percent by mass of an element by using the formula weight of a compound. So I'll explain how that works using this formula in a second. It's just another percentage formula, but I want you guys to copy this equation down, and then I'll show you guys how to use it in about a minute or so. All right, so in 3.3, it tells us to find the percentage of carbon and oxygen by mass inside of CO2. So the first thing you want to do is you want to take a look at CO2, and you want to find the formula weight of that substance. Okay. Another way of saying this is find the AMUs, find the molar mass, whatever. Okay. So we're going to take a look at our periodic table and find the the formula mass of CO2. Okay. So now we're going to be using the number on the bottom. So if we take a look at CO2, it's made out of 1 carbon and 2 oxygens, right? So carbon is 12.01, but you can always round carbon to 12. And oxygen is 16. Okay, so that means that CO2, the formula weight will be 12 plus 16 2 times because it's CO2. Okay, so your formula weight of CO2 is going to be 44 AMU. Okay, and that's going to be this number right here. I'll try my best to color code this for you guys. Okay. So again, whatever term you like, formula weight, AMU, molar mass, that's going to be how you find the formula weight. Okay. So far, so good? Okay, let's figure out the formula mass. Let's do carbon. I'll do carbon with blue and then oxygen with black. But let's do carbon first. So we're going to find the percentage of carbon first. Now, if you take a look at CO2, first thing you want to do for the numerator is the number of atoms of that element. So how many carbons are inside of CO2? 1. So we just do 1. That's the first parenthesis. And then you want the atomic weight of the element. What is the atomic weight of carbon? Yeah, 12. So 12.01 or 12. And then just divide it by the formula weight, so 44. And then you're going to multiply that by 100%. And that will give you the percentage of carbon by mass inside of CO2. Basically, what that means is if you have a CO2 molecule, how much does just the carbon weigh inside of it? What's the percentage of the weight that comes from carbon? Yeah.
So do we use like the average world atoms, like would water be 18 or 18?
18. We can use 18, yeah. If you do 18.02, that's fine as well, but it's not gonna make a big difference. Yeah. So we can punch this into our calculator and then we'll be all done with that. So let's pull out our calculator. So 1 times 12 is 12, divided by 44 in the numerator, times 100. And so what carbon is going to take up a 27.27% by mass. Okay, so if you have a carbon dioxide molecule, so everybody breathe in, breathe out. So the CO2 you breathed out, 27% of that was carbon. Okay. I know, riveting. All right, we can do oxygen the same way. So you guys don't need to copy this down. I'm just gonna do this one with you. But there are 2 oxygens. They weigh 16 each, divided by 44 times 100%. So you can do it that way, or you can look at CO2 and be like, okay, there's only carbon and oxygen in there, right? So 100% of the weight is the whole molecule. Carbon takes up 27.27. So that means oxygen must take up 72.73%. You can just subtract it. Either way works. So the carbon dioxide you just breathed out, 27% of that was carbon. And then about 73% of that was oxygen. Okay. And that's it. That's how you find the mass percentage. And again, if you can do this with your own formula that works in your brain, then just use that formula. Okay, but this is just how I'm going to teach you. All right, any questions on 3.3? Okay, I'm going to give you guys about 3 minutes. I want you guys to do 3.4. I want you guys to find, so I'm going to scroll down in just a second, but I want you guys to find the mass percentage of carbon, hydrogen, and oxygen in fructose. So this is sugar. The formula right here is sugar. And I'll write it a little bit bigger for you guys so you can see it. But sugar is C12H22O11. Yeah, I want you guys to find the mass percentage of each element in sugar. Okay, so take about 2 minutes to do that, and then we'll go over it together. Okay, so I'm just gonna skip a lot of the stuff. If you have any questions on how I got these numbers, please stop me so that I can explain. But for the formula mass of sugar, you should have gone 342 AMU. Everybody got that? Okay. If you got some decimal points because you added the 0.01, so that's totally fine as long as it's close to 342. Okay. All right, let's start with carbon. I'll do carbon in blue again. But if you take a look at carbon, there are 12 carbons inside of sugar. Okay, they each have a mass of 12 AMU. you divide it by the 342 AMU, and then you multiply that by 100%, and that should give you about 42.1% carbon. Okay. Everybody got something similar?
If you're not sure which ions you did,
What do you mean? Which ion?
like say I'm using like indium, which has 114.82. Would I like round?
Keep the 114.82.
Okay.
Yeah. So carbon is one of the weird ones where since there's like other rules, I'll probably mention them later. But if you have a 0 in the 10th place, excuse me, you can round down. But if you have something like, I don't know, like 7.9, if you have a 9 in the 10th place, you can round up. But if not, then keep it with the decimal points. Good question. Do you have a question, Aiden?
I was just gonna ask if we had 0.01.
Yeah, 0.01. So carbon, hydrogen, nitrogen, those ones, just drop them. I always drop the 0.01s. Any other questions? Okay. All right, let's go to hydrogen. Hydrogen, there are 22 hydrogens inside of sugar. They each have a mass of 1 AMU. So I guess you could ignore that. It's just 22. Divided by 342 AMU times 100%, and that'll give you about 6.4%. Okay. So even though you have the most hydrogen atoms, because they weigh so little, the mass is only going to be 6.4%. And then you can do the same thing for oxygen, but I'm just going to give you guys the answer. It should get 51.5%, around there. Okay. Alrighty, mass percent. Isn't this fun, guys? If you love chemistry, I hate chemistry. I don't know, dude. Could have done something else. Could have taught Korean. Could have played StarCraft. Which was to do chemistry. Yeah. 아니. That means no in Korean. See, I taught you Korean now. Professional ping pong player. What else are Koreans good at? Professional archer or speed skater. That's the best one. Dude, Koreans are so good at speed skating. It's weird. Badminton's just Asians, dude.
Did you win the skeleton race?
Dude, I don't know. I'm not Korean, dude. My friends call me a banana because I'm yellow on the outside but white on the inside. Because I grew up in the States, like my whole culture is like American culture. Yeah, it's really hard for me to like relate with people in Korea because like I just don't understand them. Me?
Yeah.
Cyprus here. SoCal, yeah.
Why not you grow up here?
Yeah, I'm total like SoCal person. I'm not a Korean.
How did you like the
Huh?
How did you end up like
Yeah, so that came because that's when I started watching basketball. They were like the big team. But anyway. All right, enough about me, guys. I'm not that interesting. You know what is interesting is the chemical mole. All right, so let's go into the chemical mole. So you guys might have heard the term mole. It's not that ugly little animal that lives in the ground. In chemistry, mole is a way that we count things, just like how we use dozen to count eggs, right? Pairs to count shoes. We use a mole to count atoms and molecules. And the reason why we use moles is because atoms are so small that we need to count them not 12 at a time, not 100 at a time, not 1, not 2, not 3, not 4, but we got to count them this many at a time. Okay. All right. So I'm going to teach you guys how to use this conversion real quick. And then that'll pretty much be it for today. Okay. So make sure you guys copy this conversion down if you guys don't have it memorized. 6.022 times 10 to the 23rd. It's called Avogadro's number. Sounds like avocado. Okay. And then what we're going to do is we're going to go through a couple practice problems where we go through how to convert from atoms to moles. Okay, and vice versa. So let's do 3.5 together, and then I'm going to have you guys do a couple more on your own, okay? So 3.5 is asking how many Fe molecules are inside of 1.2 moles of iron. So that means our starting number is 1.12 moles. Okay. So that is our starting value. Now, what do we want to turn moles into? Atoms, exactly. When you see a mole, guys, you want to vaporize it and turn it into atoms because they're such ugly animals. Okay, so we're going to set up a fraction. And then we're going to set up a conversion. So since we have moles on top and we want to get rid of the moles, where should we put it on the fraction? The bottom. Okay, so we're going to put moles on the bottom. And this is our conversion factor. What's the number we put next to moles?
1.
1. Good. All right, next we want to find atoms. So we're going to put atoms on the top. So that's going to be our conversion factor, 6.022 times 10 to the 23rd. Okay, and then from here, you guys should notice all we need to do is multiply those two numbers. So I want you guys to practice using your calculators a little bit. You guys can use the method that I taught you last time with the normal numbers and whatnot, or if you have a fancy, nice calculator that lets you do scientific notation, then you can use that and thank your parents for buying you a nice calculator. So I'll give you guys about 30 seconds to do that, or the person that you stole it from. Hey, you got that? We got that in recording, dude. I'm gonna record you guys, thieves. All right, so you guys can try that out and then get your final answer. Double check with your neighbor if it looks good. You guys can get started on 3.6, and then in about a minute or so, I'll give you the answer, and then we'll go over 3.6. Okay? Yes. But if you take a look at this problem, it starts off kind of normal, right? You got your starting number of 4 moles. Okay, you got 4 moles of MgNO32. So I'm gonna actually label it, just to make it more clear for you guys. And then it's asking you to turn it into individual NO3 minus ions. Okay, so we're gonna start off just by converting the mole by vaporizing these ugly animals into ions. Okay, so let's start with 1 mole. Okay, so if you have 1 mole of MgNO3, okay, same conversion rate. That means you have 6.022 times 10 to the 23rd MgNO3, and this is more like molecules, right? Okay, so far so good, guys. Does this make sense? Now, this might be where a lot of you guys stopped, but this is where you need to keep going. Because if you take a look at the formula for MgNO32, how many NO3s are there? 2. Yeah, and that's where I try to trick you guys. Because we're looking at when you have 1 MgNO32 molecule, there are a total of 2 NO3 minus ions. You guys notice that? Because the question's asking you to find NO3. And so whatever answer you get, you're going to have to multiply that by 2. Okay, so just be very careful with what you're being asked to find at the end of the problem. Let me kind of go over it just to clear things up. Our starting number is 4 moles of this compound right here, magnesium nitrate. Okay, you start with 4 moles of magnesium nitrate. You turn moles into the molecules of magnesium nitrate. But the question isn't asking for magnesium nitrate, it's asking for nitrate ions. And if you look at the formula, there are 2 nitrates in every single magnesium nitrate molecule. So you have to do this final fraction right here where you multiply it by 2. Okay, so that's somewhat of a trick question, but also kind of my way of communicating. Make sure you guys read the question carefully. Okay, and I'll give you guys the final answer here on the left. But for your final answer, you should get 4.82 times 10 to the 24 nitrate ions. Okay, something around there. Okay, so it says our starting number is 3.5 grams of carbon dioxide gas. Okay, so we're going to start with 3.5 grams of CO2. Okay, and then we want to turn it into molecules. So I'm just going to very quickly give you guys the conversion factor. So the first conversion is going to be from grams, and you want to turn it into moles. Okay, we get this number by finding the molar mass of CO2. So if you go on the periodic table and look at CO2, carbon has the number on the bottom. The molecular weight is 12. and then oxygen is 16 twice. We already did this one. So you get 44 grams in 1 mole. So that's how you turn grams into moles. Okay. Next, we're going to turn moles into molecules by multiplying by Avogadro's number times 10 to the 23. And that's going to be your setup. Okay. So your final answer for that should be about 4.79 times 10 to the 22nd CO2 molecules. All right. So I'll end right there.